So a quick reminder of the Laplace transform. This function is going to take in functions of t and spit out functions of some new variable s. And the way we're going to do this is by using an improper integral. So for all s where the improper integral converges, the Laplace transform of the function f of t is going to be the improper integral from 0 to infinity of e to the negative st times this function f of t dt. So as long as this improper integral converges, our Laplace transform f of s is defined. Notice that we're integrating with respect to t, and we have these two variables s and t appearing in the improper integral. So since we integrate with respect to t, this produces a function that is strictly in terms of s. So this is the definition that we're going to be using today. Okay, so in these videos, we're going to show a couple of examples using the definition. You have sheets containing this information. You'll be allowed to use them on quizzes and exams, but at some point, I'll expect you to be able to use this definition. Okay, but the expectation is that, like when you're working on your homework, you'll have your sheet out. You can use it. That's totally fine. But I do want to try out this definition. So if we're taking the Laplace transform of the constant function 1, what we want to do is calculate the improper integral from 0 to infinity of our function 1 times e to the negative st dt. And we want to do this integral. So first off, this thing is improper, which means that we have this, that the domain of integration is big, so we're going to use a limit. So we've got the integral from 0 to t of e to the negative st dt, and we'll let t go to infinity and see whether or not this converges. To do this integral, you can use a variable substitution. Remember that the thing we're integrating with respect to is t. So we see that our integral is going to change to this integral of negative 1 over s e to the u du, or negative 1 over s e to the u. And we can change back. So it's easy to find an antiderivative here. Okay, so we're taking the limit as t goes to infinity of negative 1 over s. To help us understand this, I'm going to put the power in the bottom and e to the st, and then minus negative 1 over s e to the s times 0. Okay, and as t gets really big, as long as s is greater than 0, this first term, as long as s is bigger than 0, this first term is going to go to 0. And our second term is just 1 over s times e to the 0, or 1 over s times 1, which is our final answer. This is true for s greater than 0. So the resulting function is one that's only defined when s is positive. Let's try out another. Next, we're going to try a slightly more complicated example. We want to take the Laplace transform of the function cosine of t. We're going to show that it's equal to s over s squared plus a squared, again, when s is greater than 0. Okay, so we use our definition of the Laplace transform, which is that we're going to be integrating from 0 to infinity cosine of t times e to the negative st dt. Okay, so this integral isn't too bad. We are going to start just by calculating the antiderivative. So we're going to find the integral of cosine of t e to the negative st just to begin with. Okay. When you look at this, you can see that we have these two unrelated pieces multiplying together, and both of them are easy to integrate and differentiate. So if you think way back to Calc 2, we had a technique called integration by parts, which said that if you have these two functions, u and the derivative of another function, this is equal to u times v minus the integral of v times the derivative of the first function. Okay, so in this particular instance, we're going to use integration by parts twice and algebra to solve for this integral. This is probably your least favorite part of the integration by parts section. So I'm going to use just a shorthand called tabular integration. Basically, if you remember, whenever we want to do integration by parts, the one piece that you differentiate, you always keep differentiating, and whatever piece you integrated, you keep integrating. So what we're going to do is just differentiate one piece and integrate the other piece, and I'll show you how to write this down. So because we're going to see that the second time we do an integral using integration by parts, it's going to be behind this negative sign. We're going to keep track of which integral we're working on, how many times we've used integration by parts, by using these plus and minuses on the right. They just switch back and forth between plus and minus. It doesn't matter which piece we choose to differentiate, which piece we choose to integrate. So let's differentiate e to the negative st. And let's integrate cosine of t, both of these with respect to t. So we're going to do it twice. Derivative of e to the negative st is going to be negative s e to the negative st, and its second derivative is going to be s squared e to the negative st. The integral of cosine of t is sine of t, and the integral of that is negative cosine of t. So the part that we're differentiating is playing the role of u, and the part that we're integrating is playing the role of dv. Okay. So we can write down our integral. This is going to look like our u times our v, so e to the negative st times sine of t. So we multiply, we use the sine and then the diagonal product. We use the sine and then the diagonal product. Okay, minus negative s e to the negative st times negative cosine of t. And then we're going, for our final step, we add the product. Here this is like a v and a du. So this is going to be plus the integral of s squared e to the negative st times negative cosine of t dt. Okay, and this is looking pretty good. I'm going to simplify the pieces on the right-hand side that are outside of the integral, and I'm going to bring together I'm going to pull out the constants from inside of the integral on the right side. So we see this s squared, which doesn't depend on t. We see this negative sign that can be pulled out front also. Okay, so here we have this simplified version. What I've done is I factored out e to the negative st from both of these terms that are outside of an integral. I consolidated these negative signs. We had 1, 2, 3 negative signs to just a single one. And this s squared and the negative sign got pulled out from inside of the integral. Notice what we see now. We have this integral on the left-hand side. It also appears on the right-hand side. So what we can do is solve for that integral. So by adding the copies of s squared cosine of t e to the negative st dt to both sides, this gives us a factor of 1 plus s squared in front of this integral. And then we know what the right-hand side is equal to. It doesn't have any integral in it. And so we are all done. We can just divide both sides by 1 over s squared. Or 1 plus s, divide both sides by 1 plus s squared. Okay, so we found our integral. Now we are ready to find the improper integral. Okay. So we're going to do that on the next slide. We are looking as t goes to infinity and comparing it to the value at when t is 0. Okay, so our Laplace transform is this improper integral. We've already found the antiderivative. So we can write down that our Laplace transform is equal to the limit as t goes to infinity, where I'm going to plug in capital T for each of these t's in our antiderivative. I'm going to pause for a second to do. And we're also going to plug in t equals 0 here. So that's going to look like 1 times sine of 0, which is 0, minus s times cosine of 0 over 1 plus s squared. Okay. All right. Now, if we're looking at this guy, this e to the negative st, you can think of this, rewriting this living in the denominator. We've got an exponential in the denominator. Sine and cosine are, moving around, but as long as s is positive, this limit is going to go to 0, because exponentials get way bigger than either sines or cosines. So we can think of rewriting this so that we can see that exponential down in the denominator. This exponential is going to be getting really, really big, so our term is going to approach 0. And our second term looks like minus negative s over 1 plus s squared, where we're just evaluating sine of 0. 0 cosine of 0 is 1. And so in our final steps, we get 0 plus s over 1 plus s squared, which is what we were hoping for. And this holds as long as that exponential lives really in the denominator, and so that holds when s is greater than 0. All right, so now that we've done this, we don't need to redo it every time. We can use this formula, but this is where it comes from. Good. Okay, we're going to try one more type of problem, which is if we're given a piecewise function and we want to find its Laplace transform. So here we're given this this piecewise function. We're going to use our definition. So the Laplace transform of this function is equal to this improper integral and if you recall, whenever we have to do an integral with a piecewise function, what we do is we break up our integral into pieces, right? So what we're going to do is break this up with one piece per definition of the function. So from 0 to 1, our function f of t looks like the 0 function. Between 1 and 2, our function looks like the t function. And then from 2 to infinity, our function looks like the constant function 1. So what we're doing is we're replacing f of t with the appropriate piece based on the interval that we're looking at. Okay, so between 0 and 1, we look like 0. From 1 to 2, this guy gets looks like t, and from 2 to infinity, our function looks like 1. Then we're going to find each of these individual integrals one by one. So 0 times anything is just 0. So the area underneath the curve 0 is just 0. So we lose this integral right away. This is just 0. Now we have these two separate integrals that we can do one at a time. So let's start with the first one. We're going to start with this integral from 1 to 2 of t e to the negative st integrated with respect to t. Okay, so again, we have a product here of unrelated pieces, so we're going to use integration by parts, and we're going to choose to differentiate the polynomial piece. So in our case, we've got u equal to t, and dv is going to be equal to e to the negative st dt. So we're going to integrate this and we're going to differentiate t. So du is equal to dt, and our v is negative 1 over s e to the negative st. Okay, so we can rewrite our integral as u times v, so negative t over s e to the negative st minus the integral of v du, so minus 1 over s e to the negative st dt. Okay, and we can simplify this a little bit more. We've got two negatives, so this becomes plus 1 over s, the integral of e to the negative st dt. Again, we can always use a u substitution to do this integral. This one is pretty straightforward though. So we end up with minus 1 over s squared e to the negative st. Okay. So if we were to write this together, we could factor out negative e to the negative st. And then we've got t over s plus 1 over s squared. Okay. And we want to evaluate this between 1 and 2. So first we're going to plug in t equals 2. So that's going to be negative e to the negative 2s 2 over s plus 1 over s squared. So this is the antiderivative at the upper bound minus the antiderivative at the lower bound. So that's going to be minus minus or plus e to the negative 1s times 1 over s plus 1 over s squared. Okay. Great, let's try the next integral. Okay, so next we have this improper integral to do. We're integrating from 2 to infinity e to the negative st dt. So integrating with respect to t. So let us rewrite this as a limit. We've got the limit as t goes to infinity of the integral from 2 to t of e to the negative st dt. We are going to find the antiderivative. Again, you can use variable substitution here, or this one you might feel comfortable doing in your head. And then we're going to be evaluating at 2 and at capital T. So we've got the limit as t goes to infinity of negative 1 over s. And I like to rewrite this as 1 over e to the s capital T. We have minus minus or plus 1 over s e to the negative 2s. Okay, now as t goes to infinity, this exponential in the denominator is going to get really, really big, which means that our first term here is going to be headed to 0. Okay, so this final limit is just going to be 1 over s e to the negative 2s. Okay, all right, so putting these different pieces together, we arrive at the Laplace transform that we were looking for. Okay, so all we've done is we've recorded our answer for the first integral, our answer for the second integral, and then I just cleaned them up a little bit. So I factored out the common exponentials in both of these terms, and then noticed that we had a common factor of 1 plus 1 over s. So gathered those together, and here we arrive at our final answer. Good job, folks.